This is SpaceTime, Series 25, Episode 63. Coming up on SpaceTime, new evidence on Earth of an ancient supernova, preparing for an Earth observation satellite mission, and India's manned space program reaches another milestone. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
New chemistry forensics suggests that a meteorite named Hypatia, which was discovered in the Egyptian desert, might be the first tangible evidence found on Earth of a thermonuclear or Type 1a supernova explosion. These are rare supernovae and are some of the most energetic events in the universe, stellar explosions so powerful they briefly outshine an entire galaxy. The findings, reported in the journal Icarus, are based on a new study of a fragment of the highly unusual Hypatia meteorite. Thermonuclear or Type 1a supernovae mark the total destruction of a sun-like star. Now, these are stars that were in binary systems with a close companion star. Stars will spend millions to billions of years slowly fusing hydrogen in their core into helium. It's this process which makes stars like our sun shine. It also provides what's called hydrostatic equilibrium, a sort of balancing act which pushes outward against the force of gravity which is trying to collapse the star. But once the star runs out of core hydrogen, the fusion process stops and gravity wins, causing the star to contract. Now, as the star contracts, eventually it builds up enough pressure and temperature in the core to allow the helium there to begin fusing into carbon and oxygen. At the same time, a thin layer of hydrogen outside the stellar core begins to burn, causing the star's outer layers to expand. And because these outer layers are now further away from the core, they're also cooler, turning the star into a red giant. Eventually, the star's core will run out of helium, and since these stars aren't massive enough to fuse carbon and oxygen into heavier elements, the nuclear fusion process stops and the star dies. Its outer gaseous envelope eventually floats away, exposing its white-hot stellar core as a white dwarf star, an object about the size of the Earth, which will slowly cool over the eons. And this will be the fate of our own star, the Sun, in about 7 billion years from now. But sun-like stars, which become white dwarfs in a binary system with a close companion, have a very different fate. Their immense gravity draws material from their binary companion. And if enough of this material builds up on the surface of the white dwarf, it can reach a sort of tipping point known as the Chandrasekhar limit, about 1.44 times the mass of our Sun. This tipping point triggers a thermonuclear explosion so powerful it destroys the entire star. And this is where the Hypatia stone comes in. The study's authors Jan Kramers, Gregory Belyanin and Hartmut Winkler, all from the University of Johannesburg, together with their colleagues, have been uncovering a series of highly unusual chemistry clues in a small fragment of Hypatia. They suggest the supernova explosion of this white dwarf happened inside a gigantic dust cloud nebula. After cooling, the remaining gas atoms of the supernova started sticking to the particles of the dust cloud, eventually forming Hypatia's parent body. Kramer says that a huge bubble of this supernova dust and gas atom mix never interacted with other dust clouds. Instead, after millions of years, the bubble slowly solidified during the early stages of formation of our solar system, some 4.6 billion years ago. He says the process probably happened in a cold, uneventful part of the outer solar system, most likely the Oort cloud or Kuiper belt. But at some point, Hypatia's parent body made its way into the inner solar system and was caught up in Earth's gravity, finally slamming down into the Great Sand Sea of southwestern Egypt, where it was eventually found. The heat of entry into Earth's atmosphere, combined with the pressure of impact, created micro-diamonds and shattered the parent rock. The Hypatia stone picked up in the desert must have been one of the fragments of the original impactor. Kramer says if this hypothesis is correct, it means the Hypatia stone will be the first tangible evidence on Earth of a Type 1a supernova explosion. Perhaps equally importantly, it shows that an individual anomalous parcel of dust from outer space could actually be incorporated into the solar nebula from which our solar system was formed without being fully mixed in. However, all that goes against the conventional view that the gas and dust from which our solar system was formed was thoroughly mixed. To piece together Hypatia's story, the authors analysed the stone in detail. Back in 2013, a study of argon isotopes first confirmed the rock wasn't formed on Earth. It had an extraterrestrial origin. Then a 2015 study of noble gases in a fragment of Hypatia indicated that it wasn't from any known type of meteorite or comet. And in 2018, the authors reported the discovery of the mineral nickel phosphide not previously found in any object in our solar system. Meanwhile, another study using a proton microprobe examined 17 carefully selected targets of Hypatia, which were chosen because they hadn't been contaminated by Earth material. This allowed the authors to identify 15 different elements in the meteorite. They found surprisingly low levels of silicon. The silicon, along with chromium and magnesium, made up less than 1% of what would have been expected to be there of something that was formed within the inner solar system. Yet at the same time, they also found higher levels of iron, sulfur, phosphorus, copper, and vanadium. This consistent pattern of trace element abundances was completely different from anything in our solar system. That meant the authors would have to begin looking outside the solar system. Kramer compared the Hypatia element concentration pattern with what one would expect to see in the interstellar dust between the stars within our local arm of the Milky Way galaxy. But again, there was no match. So this meant Hypatia didn't come from Earth. It wasn't from any known type of comet or meteorite, it didn't form from the average inner solar system dust, nor did it form from the average interstellar dust. The next simplest possible explanation for the element concentration pattern in Hypatia would be a red giant. Red giant stars are common in the universe, but the proton beam data earlier had already ruled out mass outflow from a red giant. See, Hypatia had too much iron, too little silicon, and far too low concentrations of elements heavier than iron. The next possible suspect was a core collapse or Type 2 supernova. These are produced when stars far more massive than the Sun die at the end of their lives. Because they're bigger than the Chandrasekhar limit of 1.44 times the mass of the Sun, they blast off their outer layers, but their cores collapse inwards under the force of their own gravity, resulting in a superdense object just a dozen or so kilometres across called a neutron star. Now that's the rule that applies for progenitor stars between say 8 and 20 times the mass of our Sun. Even more massive stars are so huge they collapse down beyond the neutron star stage, creating stellar mass black holes. Now, core collapse or Type 2 supernovae do cook up a lot of iron, but not as much as they found in Hypatia. And it also couldn't account for the nickel phosphide they found, and the iron to silicon and calcium ratios were also wrong. Now, all this left the much rarer Type 1a thermonuclear supernova, and they only happen about once or twice per galaxy per century. But the thing is, they do make lots of iron. In fact, they made most of the iron in the universe today. Most of the steel on Earth was once an element created in a Type 1a supernova explosion. So too is the iron in your blood. Also, some Type 1a supernovae have very distinctive chemistry because of the way they're set up. The white dwarf that explodes in a Type 1a supernova isn't just blown to bits, it's quite literally blown into atoms. What it means is the authors couldn't find a better fit for the chemical composition of a Type 1a supernova than what they have in Hypatia. Altogether, 8 of the 15 elements analysed conform to the predicted ranges of proportions relative to iron. Those are the elements silicon, sulfur, calcium, titanium, vanadium, chromium, magnesium, and nickel. However, not all 15 of the analysed elements in Hypatia fit the predictions. In 6 of the 15 elements, proportions were between 10 and 100 times higher than the ranges predicted by theoretical models, namely aluminum, phosphorus, chlorine, potassium, copper, and zinc. Kremers says that since the white dwarf star was formed from a dying red giant, Hypatia could have inherited these element proportions from a red giant. Now, if this hypothesis is correct, it means the Hypatia stone would be the first tangible evidence on Earth of a Type 1a thermonuclear supernova, one of the most energetic events in the universe. This is SpaceTime. Still to come, preparing for an Earth observation satellite mission, and India's manned space program reaches another milestone. All that and more still to come on SpaceTime. Europe's highly successful Copernicus Earth observation program is designed to monitor the environmental changes the planet's been undergoing as it continues to be affected by global warming. And the Sentinel satellites being launched as part of the program are providing scientists with an eye in the sky to study the incremental impacts of climate change. The Sentinel 1A and B spacecraft provide all-weather day and night radar imaging of land and ocean surfaces. Sentinels 2A and B provide high-resolution optical imaging of vegetation, soil, water cover, inland waterways and coastal areas. Sentinels 3A and B provide ocean and global land monitoring services. Sentinel 4 will be part of a payload attached to the third-generation Meteosat weather satellite slated for launch next year. The Sentinel-5 precursor satellite, launched in 2017, was designed to fill a gap in atmospheric composition monitoring following the loss of Envisat in 2012 until the eventual launch of Sentinel-5A and B as payloads aboard the EUMETSAT Polar System's second-generation spacecraft. The Sentinel-6A provides high-precision altimetry sea level measurements, and it will be joined in 2025 by its sister satellite Sentinel-6B. Developing the advanced scientific packages used in these spacecraft is a long-term process involving lots of tests, sometimes in harsh environments. An airborne campaign was recently carried out by the European Space Agency in the Arctic between Greenland, Iceland and Svalbard to test an airborne version of an imaging microwave radiometer at temperatures of 30 degrees below zero. This report from ESA TV.
Inside the small plane at the airport of Longyearbyen, one of the most northern cities in the world, is an instrument that is helping to define a future space mission to better understand our planet. In the extremely harsh conditions of the Arctic, engineers and scientists are testing a microwave radiometer, an instrument that is able to monitor sea ice and its evolution.
The radiometer just senses, it reads basically the sea ice, so at certain frequencies. And from that, actually breaking down into several different frequencies, you can actually study the sea ice signatures. And from that, then you can infer what kind of sea ice you have. And also from that, you can infer how old the sea ice is, for instance.
The information on sea ice characteristics from this airborne campaign is being used to support the Copernicus Imaging Microwave Radiometer, one of the 6 high-priority candidate satellite missions being studied for the European Union's Copernicus system. This is a difficult activity, but necessary to be sure that if the mission is selected to go into space, scientists will be able to retrieve the high-quality data they are looking for.
This instrument that we're flying has been around for many years already, and it had to be completely renovated in order to fly again. And we're testing it now for the first time because we want to obtain the sort of data that the satellite will see later on, and really answer some scientific questions we have in the meantime. So with this data that we're going to collect here.
This is how many operational Earth observation missions are created, a policy need that leads to the development of a tool able to give the best scientific measurements. The results on concentration and distribution of Arctic sea ice will contribute to the larger question of climate change and how the Arctic environment is affected by this global phenomenon.
The sea ice is strongly changing. You can see that parts of Svalbard, which were earlier ice covered in winter, like the fjords just out here, they are not ice covered anymore. And that in the Arctic Ocean, of course, in the summer there's much less ice, and that is the very important thing to follow by the present mission, the SIMMER, which we fly for right now, and also for the future.
This Arctic airborne campaign to help prepare the Copernicus Imaging Microwave Radiometer is part of this quest to obtain more accurate data, providing hard facts on the evolution of ice coverage, one of the key elements to understanding climate change and its impact on Earth, all part of the integrated European policy for the Arctic.
And in that report from ESA TV, we heard from Scientific Campaign Coordinator Tanja Kassel and Renee Fosberg from Denmark's National Space Institute. This is Space Time. Still to come, India's manned space program reaches another milestone, and later in the science report, a new study shows that cats not only know their own names, they also know the names of all the other members of the family. All that and more still to come on Space Time. India is moving forward with its plans for manned spaceflight. The Indian Space Research Organisation ISRO has now completed a 135-second static test firing of its new human-rated HS-200 strap-on solid rocket booster. The booster engine would form part of a human-rated version of the Mark III Geosynchronous Satellite Launch Vehicle, or GSLV. The HS-200 is based on the existing S-200 strap-on booster currently used on the GSLV Mark III. This is a 44-metre-tall three-stage medium-lift launch vehicle capable of carrying 10 tonnes into low Earth orbit and 4 tonnes into geostationary transfer orbit. As well as the two strap-on solid rocket boosters, the GSLV Mark III also uses a liquid-fueled core stage equipped with twin Vickers 2 engines burning unsymmetrical dimethylhydrazine and nitrogen tetroxide. And there's a cryogenic upper stage powered by a single CE-20 engine burning liquid hydrogen and liquid oxygen. To achieve a human rating, the launch vehicle requires increased redundancies in key systems and avionics, strengthening of numerous structural components and critical subsystems, and modifications of engine flight parameters to limit G-forces. India's Gaganyaan or Skycraft manned space program is based around an 8.2-ton spacecraft. The spacecraft will consist of a crew capsule and a service module. The 5.3-ton fully autonomous capsule will be capable of carrying up to 3 astronauts for as long as 7 days, flying at altitudes of 400 kilometres. The 2.9-ton service module will contain the solar panels, primary propulsion systems, orbital reaction control maneuvering thrusters, and all the auxiliary power and life support systems needed to keep the crew alive. Upon re-entry into Earth's atmosphere, the service module will be jettisoned, exposing the capsule's ablative heat shield. The final descent will be controlled by parachutes. The Gaganyaan capsule undertook an initial suborbital test flight back in 2014. At least 2 more unmanned orbital test flights are planned before the historic first human flight, which at this stage is slated for next year. We'll keep you informed. This is Space Time. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favorite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more space time, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.